Here on behalf of my team to present our project, which is automatic detection of guns from images using faster RCNN. My colleagues are Rana Al-Aqil, Jayda Shaibani, me Batul Al-Hmaili, Ragad Al-Nasir, Rahaf Al-Ataybi, and our supervisor, Dr. Hafidh bin Hidro. We came from the Department of Computer Sciences from King Saud University. Once again, a lone gunman kills unarmed civilians is a headline we've grown used to reading. Shooting accidents are happening too often these days that we got used to hearing about them in daily news flashes. What if we had an automatic gun detection system that will help in saving so many innocent lives? This is the question that triggered the idea of our project. The problem consists of taking an image as an input, then passing it to the detection system to obtain an annotated image with a bounding box surrounding each gun present in the image along with its class score. There are many computer vision problems, but in our research we are focusing on the object detection problem. In this specific problem, the system is not only able to identify different objects, but also detect their specific locations and surround each instance of the object with a bounding box along with its class score. Faster RCNN is state-of-the-art network. It has complex architecture that consists of 3 integrated networks: pre-trained feature extractor, region proposal network, and a fully connected network. The detection is done on many stages. Here I will take you through the process. First, the image is passed to a feature extractor, which is a pre-trained network that creates a feature map by encoding the image information. As you can see, the output of this process is a smaller but deeper representation of the image. The following step is generating k number of anchors. For each anchor, there are 2 outputs. The first output is the objectiveness score, and the second is the value of adjustment needed for the anchor to better fit the ground truth. This step leaves us with a large number of region proposals. We use non-maximum suppression function to choose the n best proposals to pass to the next stage. The following layer that the image is passed to is the ROI pooling layer, or the region of interest pooling layer. This layer takes each region proposal and its corresponding part in the feature map and resizes it to fit the fully collected network. Finally, for the classification part, the proposals are classified by measuring the overlap with the ground truth. If it exceeds a certain threshold, which in our case was 0.5, it gets assigned to its corresponding class. For the related work, there was Faster RCNN by Verma and others, where they tested 3 different classifiers in the Faster RCNN architecture. And there was also You Only Look Once, YOLO, by Rodrigo and the others, where they implemented YOLO model. Our contribution is training and testing 4 different feature extractors, the Faster RCNN architecture, and compare the results of gun detection with YOLO v2. These are the 4 architectures that we used and experimented with, which were VGG16 as the feature extractor, ResNet 50 as the feature extractor, and Inception ResNet v2 as the feature extractor, and finally MobileNet v2 as a feature extractor. For the dataset, we used 3,831 images obtained from Internet Movie Firearm database, which is publicly available. We split the data into 2,746 images for training and 600 for testing, and the remaining for validation. We've done several experiments in order to reach the best results. Ordered from lowest to highest, we can see that MobileNet v2 achieved the lowest mean average precision rate of 70%, whereas the model which achieved the highest mean average precision rate was Inception ResNet v2 with 81%. And ordered from slowest to fastest, the slowest model was Inception ResNet v2, whereas the fastest model was YOLO v2 with 0.0 milliseconds per image. Comparing our result with previous work done in the field, we can see that Verma and the others experimented with the classifier part of the architecture and obtained these results, where we experimented with the feature extractor part of the architecture and obtained this result. Our implementation of the YOLO model achieved 47% mean average precision rate, which is higher than the mean average precision rate achieved by Rodrigo and the others. These are examples of the images that the models were tested on. This is an image of a partially visible gun that got correctly detected by ResNet 50, Inception ResNet, and YOLO V2. And this is another example of a gun on a reflective surface that got correctly detected by all the models. Finally, to conclude, this project uses faster RCNN to detect guns and images. We trained and tested 4 faster RCNN models using Internet Movie Firearm Database dataset and compared our results with previous work. We concluded that the model with the highest mean average precision rate is faster RCNN with Inception ResNet V2 as its feature extractor. For future work, we plan to enable detection for other weapons such as knives and address the problem of guns classes where the system identifies the gun class, for example, rifle, revolver, and etc. Thank you for listening.